Yes, dear viewers, I welcome you to the class 4 of heat exchangers. Let us summarize the previous classes in a couple of sentences. In class 1, we have spoken about parallel flow and counter flow heat exchangers and also the temperature variations from parallel and the counter flow heat exchangers. For reference, you can go to the part 1 of this video. Now, in class 2, we have spoken about counter flow heat exchangers and its subclassification like mixed and unmixed flow, and also we have analyzed few of the examples for better understandings. You can refer to part 2. Coming to class number 3, that means in the previous class we have studied about assumptions made in heat exchangers analysis. That was the heading. So why did we study that assumptions? To find out the rate of heat transfer through the heat exchangers. To find out this Q, rate of heat transfer, we have studied regarding assumptions. Okay, now these are all the prerequisites for the next topic. So now to find this rate of heat transfer, we have two different methods. We have two methods. Those are LMTD and NTU. So these can be abbreviated like logarithmic mean temperature difference and number of transfer units. I repeat, logarithmic mean temperature difference and number of transfer units. So now coming to the first method or second method, whatever may be the method, we need to have analysis of these assumptions. We need to have better understandings of these assumptions. So I am repeating this again and again. Go back to part 3, revise all the assumptions. There we have something called a steady state condition and also the insulation condition. Okay, so from the steady state assumption and insulation assumption, we can apply first law of thermodynamics, which says the law of conservation of energy, and by that assumption I can say these equations like rate of heat transfer of hot fluid should be exactly equal to the rate of heat transfer by cold. That means whatever heat that is rejected by hot should be absorbed by cold fluid. And now, assuming that as an isobaric process, we will write the equation mCp dt on both the sides. That is mCp dt here for hot fluid, H indicating hot fluid, and mCp dt here on the RHS with suffixes C. Now again in that assumptions, we have 7th point, which says the product of M and Cp is heat capacity. I have replaced M into Cp of H with Ch, which says heat capacity of hot fluid into change in temperature, as it is should be equal to heat capacity of cold fluid into change in the temperature. So coming to the next point, we can also apply Newton's law of cooling. So Newton's law of cooling was actually HA into Ts minus T infinity, where H was convective heat transfer coefficient, Ts and T infinity are the surface temperature and atmospheric temperature. We'll replace H with U, where U is overall heat transfer coefficient. I repeat, U is overall heat transfer coefficient. It is not just convective, it is overall. I'll come back to this. Surface and surrounding temperature difference will be replaced by hot and cold fluid temperature difference. Now again you can go back to class 1, where we have mentioned theta 1 and theta 2 as the temperature difference, right? Similarly here temperature difference Th minus Tc is taken as theta. Now I told you I'll come back to this U. So for this is the reference, where this rectangular box here indicates the metallic part of the tube. Okay, say it's a surface of the tube. On one of the surface we have hot fluid, on the other surface we have cold fluid. So heat transfer from this hot fluid to the surface, fine, again from the surface to the cold fluid. These two are convection, but here in the middle we have conduction. So if I say overall heat transfer coefficient, it is the reciprocal of total resistance, where RA is the resistance offered by the side A, surface A, okay, RB is the resistance at the surface B, and R of conduction is the resistance over here. Now usually in the numerical this may be equated to 0 if data is not given, okay, if data is not given, fine. So now here, since the length of the tube is very high compared to this thickness, usually this will be neglected. But however, we will always speak about overall heat transfer coefficient, but not H. Fine. So these are the prerequisites for my derivation part. Okay. Thank you.